So these packets will be handed in when we take our midterm. So there's 2 days of the midterm. One is calculator day, one is no calculator day. So if we have 4 packets, I don't know for sure what we'll have, but if we have 4 of them, we might have 2 of them in on the first day and 2 of them in on the other day. And then you'll get some points for each of those. I think in the past I've done 6 or 7 points per packet, totaling to like 25, 28 points, somewhere in there. So almost like a quiz grade, another quiz grade. It's mostly effort, but it's a lot of, but it's also, I'll go in and I'll pick a few problems in each packet and double check them a little more carefully to make sure they're worked out right. You show your work and all that stuff. So I'll do that as well. So when you're doing these in the packet, you want to show your work. You want to work them out as if they were free response questions where you were being graded, on your work and so forth. Now, when it comes to the actual test, you're not on the multiple choice. Your work won't be graded. I mean, you can show any work you want. That's more for you. The multiple choice will just be graded right or wrong. Okay, probably on a scan sheet. The free response part, however, is just like a regular test. You get points for showing different things and so forth. So that's just like normal. But on this review, the purpose of these packets is to review and get ready and to understand what you're doing. And so I want you to show that work. So that's something I'm going to be looking at when I go through and when we hand these in. Okay. So you want to stay up with them. You may even get a chance, like tonight. I don't think the homework's very long. As a matter of fact, we might even get it done in class today, or you might even get it done in class today. So it would be a good time to work ahead in the packet, just doing the circle parts as much as you can. Okay. Now, some of them I understand there isn't anything really to do for your work. For example, number 5 here. Okay, on number 5, if you're doing this correctly, x goes to infinity. Well, what really matters when x gets really, really big? Just the highest powers, right? And since this power down here is higher than the one up here, that means the bottom's going to get way bigger. So what's this going to go to? So I can see on this one, now I don't care if you put an A down here or if you just circle your answer here, it doesn't matter. But I can see on that one, you wouldn't have any work. Okay? So there will be a few like that where I understand when I'm flipping through, I'm going to know they didn't really need any work for that one. But there's going to be other ones where for sure you should have some work. Okay, now just for the heck of it, what if this would have been x to the 5th here? No, it'd be 1 over 10, right? Because then the x to the 5ths cancel, these don't matter, and then you'd have 10 to the 8th over 10 to the 9th, where you'd end up with an extra 10 on the bottom, and then you would have had 110, right? And so that's why they had that as an answer in there too, that might throw you off. But the correct answer for that should be 0. So anyway, if you want to come up at some point or come in before school and you've got some that you didn't know about, they're all worked out in here. They do a pretty good job of working them out, kind of explaining what's going on. So this is, now, this packet at the top, it says sample exam 1. And so I've got some other ones that don't say sample exam, they just say examination 1 or exam 1 or something. So when I reference this one, I'll be talking about sample 1. So when I talk about sample 1, we're talking about this one. If I say exam 1, that's another one. You'll see it looks a little different on the front page. All right, Andy, we got a little time here where we can do a few questions. What were some that you not sure about? Or Number 3. Okay, number 3. All right, so number 3, when I see number 3, at this point in our class, this would be one where, we haven't seen a lot like this, and I mentioned this yesterday, and this is still true, and I'll say it a lot. As we go along, as we get ready for the midterm, you're going to see problems, and this would be one of those, where we know everything we need to be able to do this problem. We just have never seen it put together quite this way. And as we go into chapter 4 here, chapter 4 is all about using the derivative. So the idea is, okay, we went through the first 3 chapters. We've learned how to do the derivative of all these different functions. Now it's going to be about using those. that knowledge. Now that we know how to do the derivative, we know what the derivative stands for, how can we apply that in a bunch of different problems? So, as we get into those problems, now it's going to be a matter of, oh yeah, I remember doing that one, whether it was in the packet or in the homework. I remember when the problem sounded like this, this was my strategy. So it's going to be a lot of strategies and problem solving and that kind of stuff as we go along. So hopefully a problem in 2 or 3 weeks, a problem like this will be easier, a lot easier than it is right now. So let's just go through it. It says a line through the origin. Well, okay, so I'm probably going to draw myself a line through the origin. Okay, so if you didn't have a picture drawn, I mean, how do you expect to do this one when, right away it talks about a line through the origin rotating, I think you need a picture probably. Okay, so there's a line through the origin. It rotates around the origin in such a way that the angle theta, which is between the line and the positive x-axis. Well, here's the positive x-axis, here's the line, so that would be theta right there. Theta is the angle between them. Now it's rotating, so actually what we have here, this is like your unit circle basically, right? You got theta, you got this line, it's rotating. I mean, that's basically what happens when we do the unit circle, is we have a line rotating through the origin, creating an angle, okay? That's what they're talking about. And this angle changes, and another name for that is theta prime, of course, with respect to t. So of course, sure, that's happening. Theta is changing. Theta starts at 0, and then it's getting bigger and bigger, right? And so theta prime would be its rate of change. All right, so then what they want us to do, which expression gives the rate at which the slope of the line is changing? So now we got to talk about the slope of that line. So we want to know how fast the slope of the line is changing. So aren't we looking for m prime here, really? Isn't that what we're trying to find? We're trying to find m prime. Now, actually, dm over dt, right? Because with respect to time, how fast is the slope changing? So we're really looking for dm dt, which we usually write m prime. They're the same thing, okay? So I need an equation for the slope. Well, when I look at the slope, here would be the secret to this problem. The secret to this problem would be drawing in a little triangle here like that. Because think about Algebra 1 class. What's the best way to find the slope? What's the quickest and easiest way to find the slope of a line if you're looking at a graph? Rise over run. Rise over run. So tell me the slope of that line right there. Well, it's changing, right? So what can I label this right here? Okay, now I like where you're going with that. You're thinking opposite. You're thinking right triangle, SOHCAHTOA kind of stuff, I think, which is good. But usually we don't label something opposite. We usually use a letter. What would be a good letter for this? Y. Would Y be a good letter? I could call it opposite. You're right. I mean, I could call it Y. I could call it opposite. Opposite would work fine. Okay, but then I was thinking unit circle, right? So in the unit circle, right, don't you have this point up here and it's got a coordinate x and y, right? But I could call this adjacent, and I could call this opposite also, okay? So what is this slope? Well, it's y over x. It's opposite over adjacent. But I don't like either one of those. What is opposite over adjacent? Tangent, because I need to get theta involved. Look at all my answers. All my answers have theta. So my equation I want is m equals tangent theta. That's the equation I want. Okay? I want that equation. Because now I can do m prime. Okay? So what is m prime? Well, m prime would be, what's the derivative of tangent? Secant squared theta. Do you see secant squared up there? Wait a minute. But wait a minute, why has it got a theta prime tacked on it again? Oh, it's implicit differentiation. Look at this. Remember, that's why I said this right here. I was kind of thinking of that before. We want m, when we want m prime, we want dm dt. We want m prime with respect to t. This is theta. So that's kind of like having a y. Every time you have a y in there, you have to tack on a y prime, right? Well, what we're doing is when we do this derivative of tangent theta, we have to tack on a theta prime. Now, again, if this is the test, I'm guessing you wouldn't have cared about that. You just noticed they all had a d theta dt at the end, and you probably was like, I don't know what that's up for. But if you could have got this far to do a tangent, you could have said, okay, the derivative is secant squared, and this is the only one that looks like that, so you could have probably by process of elimination, because remember, 65% is an A. You may be doing some guessing, right? Or at least eliminating and trying to figure out maybe the best answer. And there is no penalty for guessing. There used to be, just like there used to be, was it the SAT? SAT, I think, used to have a penalty for guessing on the multiple choice. How did they know you were guessing? They would subtract points when you got one wrong. You get no points if you left it blank, but they would subtract points if you get it wrong. Anybody ever take one of those where they did that? Where they did something like that? It's kind of an interesting math scenario. The reason, here was their logic. Their logic behind it. And the AP test used to be this way. But here was the logic behind it. Let's say you got 100 multiple choice questions. Okay? And let's say let's say, your 6-year-old brother took this calculus test. Right? What score should your 6-year-old brother get on a calculus test? Right? If it's a true measure of what they know, your 6-year-old brother should probably get a 0. Okay? But if there are 5 choices and it's all multiple choice, if there are 5 choices, theoretically, he's going to get how many wrong? How many is he going to get right out of 100? Theoretically. 20. Right? Because he's got a 1 out of 5 chance to just bubble in, the right answer. Okay? So he just does A every time, right? Theoretically, he would get 20 right. So if there's 5 choices, your 6-year-old brother get a 20. Well, that's not a true measure of what they know. So what they say is guessing, is not a true measure. So what they do is, if there's 5 choices, they subtract 1/4 of the value for each problem. So what that means is, if you answer, if your brother got 20 right, that means he got 80 wrong, right? So what you do is you take the 20, so you take the 20 he got right, and you subtract 1/4 of all the ones he got wrong. Well, 1/4 of 80 is 20. 20 minus 20, then it gives you 0. And so that was their adjustment that way. So what would happen is, when you were taking this test, if you weren't really sure, you might be better off to leave it blank. Now, you get 0 points, so you're not going to get a very good score if you leave a bunch blank. But the problem with it, I think, was people got really scared about answering questions, and even if you didn't know it, it was kind of a hassle. So they've gotten rid of that now. So anyway, on our test, we don't on our multiple choice. If you don't know, guess, right? Fill it in. Guess.
Why do you have yours?
Yeah. On this?
No.
No. Oh, I don't. No.
Why
What were you?
Why do you use tangent? Why is it not absolute?
Because slope would be rise over run.
Oh.
Right? Opposite over adjacent. Okay. All right. What else? What else? We got time. We can do a couple more. Remember, we are handing these in, and some of the problems will be graded specifically. Looking at your work. Yes, Beth. 13. All right. If the graph of f of x equals 2x squared plus k over x has a point of inflection at x equals -1, then the value of k is. These problems tend to give us difficulty, at least here in the beginning, when there's a k or an a or a b or something like that in there. And my advice is just, it's a number. It's a number. So just do everything you would if that was a 3 over x or a 7 over x or whatever. Okay? Now, where do you look? The key is point of inflection. Where do you look for point of inflection? F double prime, right? F double prime. When F double prime equals 0 is a good place to look. That's a possible inflection point. That's a good place to look. So we want to do F double prime. So I would write this as kx to the negative 1, first of all. So this is 2x squared plus kx to the negative 1. So this would be 4x minus kx to the negative 2. And then F double prime would be 4 plus 2kx to the negative 3. Correct? So k is just a constant. And that should equal 0. Right? Now, it turns out that that could be undefined as well, but typically it's not going to be one to bother. But we don't have to solve that. We don't have to find where it is. They told us. So what do we do with that negative 1? We put it in for x. So we get 4 plus 2k over, now that would be over x cubed, so that would be 1 cubed. And then we know that's supposed to equal 0 because it's a point of inflection, so probably what happens, that equals 0 there. Well, so we end up with 4 plus 2k equals 0 because that 1 is just there. And so we get 2k equals negative 4, and we get k equals negative 2. And so it would look like that. Yes? Yes, keys. Just checking. See if you guys are paying attention. Yes, it was negative 1 cubed. Right? And so that's negative. When I flipped that to the bottom, I don't know, I must have been thinking when I flipped that, then turned positive somehow. I was thinking of that, I guess. I don't know. That would be bad. So that makes that negative, and that makes that negative, and that makes that positive. And so, like I said, the choice is E. Okay. Isn't that the way it is, though? And they often, and multiple choice, I mean, that's just the way they write multiple choice questions. They're called distractors, right? There's the right answer, and then the distractors. Well, very often they take what are the common mistakes that people will make, and they put those in there. So oftentimes you'll be working along, just like great example. I'm working along thinking I did everything great. There's my answer. It's there. I must be good because my answer was there, right? And sure enough, I made a silly mistake like that. So be careful there. All right, what else? What else? I mean, by far the best value we get out of these sample exams is for you to sit there. Now, if you talk with somebody else about it, help each other, that's good. But if you struggle with them, you get them figured out, that's very valuable. But there's a lot of value in this, too, is of us going through it. So if there's anything where you thought was particularly different or difficult, let's talk. Yes? 24. Okay, the f and g are piecewise linear functions whose graphs are shown above. If h of x equals f of x times g of x, then h prime of 3 equals what? So what this reminds me of is what I used to say, before you can find h prime of 3, you've got to find h prime of... Before you can find h prime of 3, you need to find h prime of x. So what we need is to write out h prime of x. Now, how do we do that? Well, this is a what rule? Product rule. So the h prime of x is going to be the derivative of the first, which is f prime of x times g of x left alone plus f of x left alone times g prime of x. Okay? And now we want to plug in a 3. So this is going to be f prime of 3 times g of 3 plus f of 3 times g prime of 3. And so now it's just a matter of filling in each one of those pieces. So f prime of 3, so where's the f graph? F graph is this one, so at 3, so what's this slope? Looks like it's down 1, 1, 2, 3 over. So it looks like, what would that be? Negative 1/3. So this would be negative 1/3. G of 3 would be just that point right there, which is 3, plus f of 3
be this y value, which is 1. And g prime of 3 would be this slope, which looks like it's just 1. So negative 1 plus 1. Good. Okay. So product rule, and then plugging in and getting those values. 22. Now, these, and these practice tests are a number of years old now at this point, but the AP test hasn't changed a whole lot. And then I have access to some of the newer stuff that we fill in with here as we review. But a lot of this is very similar. But not that it's old notation, but the dy dx you see a lot. And we don't use that as much. But remember, dy over dx is just what? Dy over dx is just y prime, right? And what's this one with the, that's just y double prime, right? That's all it is. That's all it is. Second derivative, okay? So they're giving you y prime. So since we usually write it this way in class, I would probably rewrite it, if I was you, as y prime equals x squared, y squared. And they want you to find y double prime. So that means we got to do what? What do we got to do? Do the derivative, which it would involve the product rule. So the derivative of y prime would be y double prime. And then we got to do the product rule. So it's just like on the gateway test, a little different in that we're doing y double prime, but we do the product rule. So derivative of x squared is 2x. We leave the y squared alone. Plus, we leave the x squared alone. And then the derivative of y squared, I'm going to put the 2 in, so it'd be 2y. So I'll put the 2 in front. 2y and y prime. When you do a derivative of y, you tack on a y prime. Now, what's weird about this is it's got a y prime in it, and you look at your answers, and none of your answers have a y prime in it. So what do we need to do? Let's just substitute that for that, right? And that'll happen every single time. Every single time you do a y double prime with implicit differentiation, this is going to happen because you're going to have a y prime. It's got x's and y's in it. When you do the derivative of that, you're going to tack on a y prime. And so what's going to happen, you're going to have a y prime in here. But that's okay because you had to have a y prime before you get a y double prime. So every time this happens, wherever you see a y prime, you'll take your y prime and you'll stick it in there. Okay, so what do we get? We get 2xy squared. And then this would be 2x squared y. And then we'd have another x squared. So that'd be 2x to the 4th. And we got a y and a y squared to make a y cubed. And so that looks like that's down here. Okay, so that's a little bit of a twist that I don't know if we've done, I think we did that maybe one time. We were doing implicit differentiation, so but that's what will always happen with those when you do y double prime. All right, what else? What else? What else? One more. That's all we got time. I think we've done half of them already. Anything else? Yes. 18. Okay. If y equals x times ln of x squared, then dy dx, or that's y prime, would equal what? So now this has to be a product rule. So the squared is just on the ln x. So we're going to go derivative of x would be 1. We're going to have the ln x squared left alone plus x left alone. And now I got to do the derivative of that. Now I'm going to go over here and just kind of do this on my own off to the side here. So I got to do the derivative of this. So that would be a 2 down in front. That'd be the ln x left alone to the first. And then the derivative of the inside is 1 over x. Okay, so I'm going to have a 2. I'm going to have an ln x. And I'm going to have a 1 over x. Like that. So that will go there. Now, won't that x and 1 over x cancel? That x and 1 over x right there will cancel. So we get ln x, come quantity squared plus 2 ln x. So I look over here and I don't see that anywhere. Well, what did they do? They pulled out an ln x, which I wouldn't think would be necessary, but that's what they did. And this is what, so on the gateway test, when I made you do all this simplifying, it was for 2 reasons. And I wouldn't even consider this simplifying, this part. I would have let you just leave it right here. But we did talk about the fact that now think about what we're doing with the derivative. Usually what we do with the derivative is what? Set it equal to 0. And then have to solve. Well, if that was the case in this problem, what would you do? If you were going to set this equal to 0, sure enough, what you would do is going to take out an ln x. Okay, so we definitely have to be able to do it. And here's another reason we have to be able to do it, because we're required to do it here on, on the midterm. In the multiple choice situation, we have to be able to match our answer to what they have. Okay? I think I told you this story of kind of this one that I just see a lot, where you work out this problem, you do all this calculus stuff, no calculator, and you get your answer and it says ln 4. And that's not one of the choices. And what is one of the choices? 2 ln 2. Are those the same? ln 4 is the same as ln of 2 squared. Remember the rule with logs? If you have a power in there, you bring the power down. So ln 4 is actually the same as 2 ln 2. So you do all this work, you get ln 4 for the answer. It's not one of the choices, but 2 ln 2 is. And you got to be able to do that. Okay? It's just the way those work. All right, moving on. Let's get your, put that aside then. Let's go ahead and get that line and ranger thing out. Get your notes out. Okay, and what we were doing here when we were talking about the line and the ranger, we were just introducing the idea of parametric equations. Okay, parametric equations. And parametric equations allow us to talk about motion in 2 dimensions instead of 1 dimension. So while you're getting organized here, I'll just remind you what we did before Christmas. We were talking position, we were talking velocity, we were talking acceleration, f prime, f double prime. And a lot of our equations, a lot of our problems were a particle moving on the x-axis. Okay, so we had a particle moving back and forth on the x-axis. So if he's going this way, the velocity was positive. If it's going this way, the velocity is negative. So that was x prime. X was the position. X prime was the velocity. And he was moving horizontally. Now, if we put that same particle on the y-axis, then he's moving vertically, 1 dimension. So we have position, we have velocity, acceleration. Okay, what a parametric equation allows us to do is have 2-dimensional motion. Now we can have a particle moving on an XY plane. So we got, for example, we had the lion and we had the ranger, and they were walking like that. And this was X and this was Y. We didn't have T, we didn't have time involved. This was east, this was, this was north, and they were moving not just back and forth this way or not just up and down, but a combination of both of them. Okay, so it's the same calculus ideas though. And what we had found with the lion, do you remember? What was the equation we had for the lion? Look at the table at the bottom of the front page. For the lion, in the very bottom of the table. Remember we came up with an x equation down there, and what was it? 0.3t, wasn't it? Plus, do we have a 0? Or did we just leave it off? We just have 0.3t. Yeah, 0.3t. But I'm going to put plus 0 and you'll see why in a minute. And then we had the y equation was what? 0.1t plus 51. Right? And so what we had is, and that's because we were told that the lion starts here at the point 051, and then he goes 0.3 miles per minute this way, and he goes 0.1 miles per minute to the north. Isn't that what we were told in that problem, if you remember? Okay, so we were told, so we weren't told how fast the lion, because the lion's actually moving here, right? There's the lion's actually moving there. But we were told his eastward movement is northward movement. Okay? Now, we didn't talk about this at the time, but wouldn't this be considered the x, wouldn't x prime be the 0.3? Wouldn't that be his horizontal velocity? Wouldn't that be how fast his x coordinate would be changing? Would be 0.3 miles per minute, that'd be the rate. And then what would y prime be? 0.1. Now, look at this x prime equation, and now look at the x equation we came up with, and how do you suppose we got from x prime to x? Not derivative. Antiderivative. Doesn't it make sense that the antiderivative of 0.3 would be 0.3t plus c, and then we would need the initial condition. And what's the initial condition for x? Well, what x does the line start at? 0. And his y prime, his y velocity, his vertical velocity was 0.1 meters every minute, or miles every minute. We do the antiderivative of that, we get 0.1t plus c. His initial condition, what was his initial y value? 51. So all we're doing when we have two-dimensional motion is we're going to have two separate equations, one for the horizontal motion, one for the vertical motion. Okay, now, I would say to you that we would have, if we go back to where we had the particle just moving back and forth on the x-axis, remember those problems, right? We were talking about a particle just moving back and forth on the x-axis. So if I would have given you, don't write this down, but if I had given you a problem like this, you know, this is a particle moving on the x-axis. Couldn't I have written that as a parametric equation, meaning couldn't I have had an x and a y? What would be the y equation of a particle that's just moving back and forth on the x-axis? It'd just be 0, wouldn't it? Right? I could have that represent the situation we were talking about. Now, we want to know how fast this particle's moving. We just do x prime. We wouldn't mess with y prime because it would always be 0, so it wouldn't matter. So this particle has velocity going this way. It's also his speed. Now, again, speed is positive always, absolute value. So if he's going that way 10 mile an hour, or he's going this way negative 10 mile an hour, his speed is still 10 mile an hour. Okay? So, in a way, we could have thought of that as a parametric equation back when we were doing that. Okay, back here to the line. So now, this would be the position then. So those equations we came up with would have been considered the position of the line. And if you want to know what position when at 2 minutes, what would you do? If you want to know the line's position in 2 minutes, what would you do? Put it into where? In which equation? Both. You would put a 2 into both, right? You would put a 2 into here, and that would give you his x-coordinate. You'd put a 2 into here, and that would give you the y-coordinate. And that's what you would get with position. When we were doing just the x-axis, his position was just a single number. But now we have 2 dimensions. So now his position is an x and a y-coordinate, okay? All right. So that's position. This is velocity here, okay? So this is both the horizontal and the vertical velocity here. But then we had 2 other questions we did. Number 6, look at number 6. Number 6 on that worksheet said, how fast, what are the rates that the lion and the ranger are moving? Now, I don't know if you showed your work there. How did we calculate how fast the lion was moving? We did the Pythagorean theorem. If the lion is moving 0.3 miles per minute this way and 0.1 miles per minute this way, then we should be able to just do the Pythagorean theorem. So we did 0.3 squared plus 0.1 squared, and that gave us what? 0.36 miles per minute. That was the actual speed. So look at this. This is where it can get a little confusing. We actually have 3 different velocities on this line. Okay? This was miles per minute. This was miles per minute. And this one is miles per minute. Now, they're all valuable. This one tells you how fast he's going this direction. This one tells you how fast in that direction. But this tells the actual speed that he's traveling. okay, which is probably the most important one that we want. And notice it's bigger than either of those others, and that makes sense. And it's closest to 0.3 because that's the one that's the biggest. So he's going, most of his direction is to the right, but he's going a little bit north. So it's a pretty flat path he's on, mostly going right, a little bit north, and that's why his speed's a little above 0.3, that direction. Okay, now, so we probably could generalize that into this kind of an equation then. It looks like when we have a parametric equation, we're going to write that in our notes here in a minute, so you don't have to write it right now, but we're going to organize a little bit. But it looks like to get the speed of the particle, and this would always be positive because the square root would be positive, we just take his horizontal velocity, square it, his vertical velocity, square it, do the square root of that, and it comes from this whole idea here of Pythagorean theorem. So that's an equation we're going to have to understand and memorize. Okay, here's the last thing. What about the slope of the path that the lion is on? Now we talked about this back when we were doing this, because this is where this could be a little interesting also. We did so much talk about how slope and derivative, slope and rate of change are the same thing. But we got to be careful because there's a lot of different rates of change. Okay? So the slope here is not the same as the speed. And the slope is not the same as the velocity. The slope, what is the slope? And I think you answered that in like question 2 or 3 or something. What's the slope of this line right here? What's the slope of this red line right here? It's 1/3. It's 0.1 over 0.3, which would be 1/3. Now, that's not the speed. That's not any of his speeds, 1/3, or not one, right? But we got to think of the units. What is this unit? What is this 0.1? Miles per minute north. What is this? Miles per minute east. If you divide those, the minutes will cancel, and you end up with miles north over miles east. What this is saying is that the lion is going 1 mile north for every 3 miles east. Now, isn't that true? Isn't that what he's doing? He's going 1 mile north for every 3 miles east. That's a rate, but it's not his speed. His speed would be miles per minute. Okay? So it is a rate, but it's not his speed. So we got to understand that slope and speed are different. So 1/3 would be our slope, and the way we got that is we took y prime and we divided by x prime, right? Rise over run. Y prime divided by x prime. Now, let's do that with Leibniz notation, which helps us a little bit. So that was our slope. So what that really means, our slope is really our change in y over change in x. So that's dy dx is our slope. And we got that by doing that. You say, well, wait a minute, I thought dy dx was y prime. Not quite. dy dx is y prime, but it's with respect to x. What y prime is this? This is dy over, remember, it's miles per minute. This is dy over dt. And this is dx over dt, right? That's what this x prime and this y prime are. This is what dy over dt. This is dx over dt. It's miles per minute. Okay, so this is dy over dt divided by dx over dt. Okay, now the dt's would cancel, you get dy over dx, okay? But so it's important, I usually just write it y prime over x prime, but you got to understand it's dy dt over dx dt, okay? And that gives us the slope of the path. All right, so there's a lot of stuff right there. Let's organize it here a little bit and get this written down in a coherent way in our notes, okay? So let's go. All right, so with all that said, let's organize our thoughts here. So parametric equations. Parametric equation starts with an x and a y equation, which is going to represent position. Now it's the x coordinate and the y coordinate. So we're not talking about one-dimensional motion here. We're talking about in 2 dimensions, both horizontal and vertical. So we have an x and a y coordinate. So x and y will be the position functions, but we're going to have 2 of them, one for horizontal, one for vertical. Okay, but most of the same stuff still applies that we learned about position before Christmas. All right, Now, on the left here, I called it number 1, but so that's probably the most important thing. If we do the derivative of those, we get velocity. So you start with position. So x and y equations are position. You do the derivative of those, that's velocity. So x prime would be horizontal velocity, y prime would be vertical velocity. And then, a little out of order, doesn't really matter. The order of these does matter. And then we talked about the speed. So imagine now we got this particle moving around on a piece of paper, right? Going up, down, left, right, diagonal. His speed, the particle's speed at any given time is x prime squared plus y prime squared. So like before, we said you want to know his speed at 2 minutes. You plug a 2 in where? You plug a 2 into x prime, you plug a 2 into y prime, and then you plug those answers into this little formula right here. The square root of x prime squared plus y prime squared. And then the other little equation we have to know is the slope of the path. And don't worry about this stuff here with the line, that's just what we were just writing down. So the slope of the path is different than the speed on the path, right? Because again, you could have one path, like the track, right? The track out could be the path, you have 2 different people on the path, going at different speeds. Same path, so, and we'll do some examples of what that looks like. So dy over dx is your slope of your path, and you get that by doing dy over dt divided by dx over dt, or just what's simple to remember, just y prime over x prime. So if you want to know the slope of the path when in 2 minutes, at 2 minutes, so wherever the particle is on the path, what's the slope of the path at that point? Then you plug a 2 into y prime, 2 into x prime, and you divide them, and that's the slope of the path. All right, so we just got to know those equations. So let's take a look at an example. Okay, so we already did the line and ranger situation. Let's take a look at this example here. We're going to do 2 quick examples. Okay, so I forgot I needed to present. Let's see. I want to pick somebody ahead of time. Close, I think. Claire, let me see. Everybody, go ahead and get your calculators out. Did I pick Claire? I did pick Claire. You don't have to log in except Claire. Claire's the only one that's got to log in. Go ahead and get your calculators out, because we will be doing a lot of work with our calculators with these. With the parametric equations, a lot of it will be in your calculator. You're going to have to be able to trade. You're going to have to be able to graph a parametric equation. You're going to have to be able to. You're going to have to be able to trace on it. You're going to be plugging numbers in, like we just said. You're going to plug in a 2, and you're going to want to find x prime and y prime, and then you want to add those up and square root it, right, to find the speed. And so there's going to be a lot of this will be on calculators. All right, what's that?
The battery was just yellow.
Now it went dead.
No, it's not dead.
It's getting close. It's blinking. It's okay. Well, we'll see if it'll hold out. All right, so go to your scratch pad on the graph screen. Okay. So let's go ahead and let's delete that out of there. Or doc B, if you got a bunch of stuff, doc B will just clear out your scratch pad. That's not a bad idea right now. Just do that. Just do doc B. Hit enter. Hit enter there, Claire. Or doc B now. Just doc B should clear everything out. Okay, so now let's go back to your graph screen. Okay, and now we're going to go to menu, and we're going to go to graph entry, number 3, and we're going to go to 4 parametric. 4 parametric. And let's put in cosine t, because one of the things we talked about is the unit circle is a parametric equation. The x coordinate is the cosine of theta, the angle, and the y is sine. So we put sine here, sine t, and of course we're going 0 to 6.28, which is 2 pi. So hit enter, and we get that. Now it's pretty small, so let's change our window. So let's go to menu. Now one of the things you have to know about the window is you got three things to change, X, Y, and T. Now in the window it's only X and Y. So let's go, let's just go -2 to, let's go -3. No, let's go -2 to 2, I'm sorry. -2 to 2. And let's go -1.5 to 1.5. Okay, so there we go. So decent looking circle. And so let's trace at, let's say 1.2. So just type in a 1.2. So there you go. Of course, pi halves we know is 1.57, so 1.57 would be up at the top. So 1.2 is about right there. Now hit your right arrow, and hit your right arrow again. Look what direction it's going. It's not going right, it's going left, isn't it? Well, that's the direction this is going, right? And so keep hitting the right arrow, and it's going around, and we're tracing, and we're getting these values. And of course, if you type in, we know T is actually theta, so type in pi force. Type in pi force. And of course, look what we get. Square root of 2 over 2, square root of 2 over 2. We get that point right there. We get the unit circle, right? In a mode of parametric equations. All right. Questions? All right. Now, so that's one idea. But notice this is X and Y. T or theta is nowhere on our graph, right? That's our angle that we have there. Now, let's look at a couple of things. So let's say when we were, go back to 1.2, Claire, go ahead and trace back to 1.2, and that was up here somewhere, right? Okay, now, and this particle was moving like in this direction, right? Okay, now, let's do X prime. And you don't have to put the T. A lot of times I just write X equals cosine T and Y equals sine T. I don't put the X of T, but you can have it, doesn't matter. What's X prime then here? What's X prime? Negative sine T. And what's Y prime? Cosine T, right? Now those should be the velocities, right? Now let's do T equals 1.2. So go to your calculator screen and let's plug in negative sine of 1.2. So Claire, go to your calculator screen there for me and type in negative sine 1.2. Look what we get. Negative 0.932. So negative 0.932. And let's say that's inches per second. I don't know. But it's a velocity. Okay, now let's do cosine of 1.2. So let's plug in a 1.2 into cosine. And Claire has got 0.362 for us. 0.362 inches per second. Now let's think about those numbers. Does it make sense that the X prime is negative and the Y prime is positive? What would it mean that X prime is negative? Remember, X is horizontal. Not slow, not slow. This is velocity we're talking about. It's moving to the left. If X prime is negative, if its horizontal velocity is negative, it means it's going to the left. Now, is that particle moving to the left right now? But it's also moving up. It's moving to the left and up. So therefore, look at Y prime. Y prime is positive. So Y prime is positive, means it's going up. X prime is negative, means it's going left. This particle is going up and to the left. Now, its horizontal velocity is like 0.9, almost triple its vertical velocity. What's that mean? It's mostly going left, right? Isn't that true of the particle up there near the top of the circle? It's mostly going left right now. It's just going up a little bit. Now, early on, if we would go back down here, what's the particle doing? Mostly going up and going a little bit to the left. So we would expect those to be reversed, right? But it still would be So that makes sense? So the x prime and the y prime tell us about the movement of the particle because those stand for horizontal and vertical velocity. Okay? All right. So that's an example of what you're going to do. I'm going to give you a different scenario. I'm going to give you a parametric equation like this, and then you're going to be asked a bunch of questions about it. You're going to do x prime and you're going to do y prime, and you're going to plug numbers into it to see where its position is, see what direction it's moving, stuff like that. Okay? And you're going to be using your calculator. All right, let's look at this last scenario. One more scenario, then I'm going to let you start working. So let's say I have these two equations right here. So Claire is going to graph these for us here. And so we'll delete out the one, and everybody can do it as well if you want to. But we're going to delete out the ones you got there. And so we're going to go that's fine, x equals t, and y equals sine t. And hit enter. Now, let's change our window. Go to menu, window, zoom, and let's do zoom trig. Do 8. Okay? Oh, isn't that interesting? What's it look like? Sine graph. Now, it only gave us from 0 to 2 pi, but that's because that's how we had our t set. Okay? Now, let's come back to my picture here. And let's graph that. And so we got this graph right here. Okay? Now, that's interesting. But you know what? It's not that surprising because look at this. If x, everybody look up here real quick. If x is equal to t, couldn't we substitute and take this t out and put a x in its place? And then we get y equals sine x? We're going to talk more about that tomorrow. That's a way you can turn a parametric equation into a regular y and x equation, is by substitution. In this case, we can just substitute an x right there. We get y equals sine x. Oh, it makes sense that that's what we would get. Okay, now let's go to this one over here. Okay, so now we go to this one over here. So go ahead and hit tab, and now we want to graph them both. So we want to have both on. So leave the other one on. So now put t squared here. And then put sine of t squared here, and hit enter. And look at that, it's exactly the same graph. Is that surprising? No, because we can do the same substitution. If x is equal to t squared, then we can take this t squared out and put an x there, and we get y equals sine x. Now, let me show you what that means. What that means is these two equations have the same path, but they are different particles on the path, right? This represents one particle's motion. This represents another particle's motion. They have the same path. So like the slope equation is going to give us the same answer, right? Okay, but let's just talk about this. I mean, at different places, but at different times it'll be different because the particles will be at different places on the path. So let's talk about t equals 2. Let's see where these two particles are at t equals 2. So go ahead and, well, if we plug a 2 in here, if you put a 2 in for t here, you get x will be 2. And what we get for y, what's sine of 2? Just go on your calculator and do that for me, Claire. Just go to the calculator part. Oh, you traced, didn't you? Just do sine of 2. I'm going to do it here, but you're right, we could have just traced. But let's just do it here. Hit control enter. So 0.909. Now go back to your graph, Claire. Oh. Go back to your graph. She had traced at 2, which that's the same as plugging in a 2, right? So that's where the particle is on the blue graph. So let's write that down. So at t equals 2, on this graph, it's at 2 and 0.909. So that's like about right here, okay, on this graph. Now let's look at this graph, and let's put a 2 into there. Where is that particle on this graph? Trace it to, now hit the up arrow so you get to the blue graph. Or no, oh, I see, you already did it for me. Okay, we now want to be on the red graph. Actually, you're on the red graph here, t squared. Type in a 2 then. Type in a 2. See where that particle is there? So what's that tell you about this particle? What was it, 4 and what?
4 and negative 0.757.
So it was down here, right? What's that tell you about this particle? It's moving faster, isn't it? Because both of these dots are at 2 seconds or 2 minutes or whatever, right? So we got the same path. So these two graphs look exactly the same, but they're not. The motion is different, and the velocities will be different at different times because they're two different particles on the same path. So we plug a 2 into here, we get where this graph, where this particle is. We plug a 2 into here, we get where that particle is. Okay? And so sometimes that would happen. And then, of course, if we did our x prime, we'd have x prime and y prime would be different here than they are here. And that's why we would get different velocities, right? At different times. Okay, so what you're going to work on here today is this little worksheet here, and you can work on it together. You can see at the top there, it's got an equation. We got atom ant. Atom ant is going to be crawling around on the XY plane. Just imagine him crawling around on a piece of paper, whatever, according to these two equations. So, they tell you to plot this on your grapher. It says use a window, -5 to 5 in the x, -2 to 5 for the y, a t range of 0 to 4 pi, so they tell you what to set your window for. Then they want you to, well, you can pretty much read what they want you to do, okay? And they want you to zoom in on the graph at certain points and look at his motion and how he's moving around, okay? And so forth. So that's basically your homework for tomorrow, is to go through this worksheet, okay? Now be careful, you can let the calculator do the derivatives for you, but you need to put a time sign in between this 0.4 t and this cosine, because if you don't put a time sign between the t and the cosine, it's going to think that's all those letters go together, okay? So you got to put a time sign in between them.